Learning Outcome 810. Describe and draw the block diagram for modulation and demodulation for pulse amplitude modulation. With Learning Outcome 8.6, determine the spectrum for all signals in an amplitude modulation process. And Learning Outcome 8.11, draw a block diagram for time division multiplexing and demultiplexing. Back at the beginning of Chapter 8, we discussed sinusoidal amplitude modulation, where we take our signal and we multiply by or modulate by a sinusoid, usually a cosine. And this produced a signal with alternating amplitude that followed the envelope shape of our original signal. Now, we're going to replace our sinusoid with a rectangular pulse. You'll find the signal in Table 4.2, and you have used it a few times, particularly back in Chapter 3 when we did things with Fourier series. So now the signal that results will be different. What will it be? Well, note that the amplitude of this rectangular pulse train is 1 in certain regions. And therefore, if we again look at the effect of multiplying our original signal by just rectangular pulse, where we have 1s in our modulating signal, we will have x of t in a resulting signal because 1 times x of t is x of t. So in this region, we will have an amplitude of x of t in our resulting signal. Likewise, in this region, we will have an amplitude of x of t in our resulting signal. And here, x of t as well. And that x of t is varying within those regions. Note also that we have regions which are 0 in amplitude in our modulating signal. So in those bands, we will take our x of t and multiply by 0, which gives us an output value of 0. So in this region, our result will be 0. In this region, our result will be x of t. Then 0, then x of t, then 0, then x of t, then 0, etc. And we'll wind up with this sort of resulting signal. This is drawn slightly elevated just for visualization purposes. It really has an amplitude of 0. So it will follow the shape of our signal, but only be on at certain times. So what about the spectrum for this? Our original signal, again, we assume it is band limited. And now we need to look at the Fourier transform of this signal. Again, Table 4.2. We have again impulses. Where are they spaced? There's going to be an infinite number of them located at multiples of omega naught. What's omega naught? 2 pi divided by t. What's t? T is the period of our function. And by what will those impulses be scaled? Do you recognize this function? You should. It's a sinc function. So these will be spaced omega naught, or 2 pi over t apart, with amplitudes that follow a sinc pattern. Previously, we only had 2 impulses. So after convolution and applying the sifting theorem with some linearity, we only had 2 resulting triangles. Now, we have an infinite number of impulses, so we'll wind up with an infinite number of triangles. And these are drawn squished just so I can show you several of them. And you can again see that it follows this sinc pattern. So if this is our spectrum and this is our time signal, how do we get our original signal back out? We're going to look at it in the frequency domain. We're trying to get that triangle back, triangle that's located at 0. If we expand this a little bit, we've got a triangle located at 0. So all we need to do is apply a low-pass filter with the appropriate bandwidth. We want to go out as far as omega m plus a little bit, And that will throw away the remaining parts, and we'll have just this one triangle returned. Pretty simple. Let's look at this again. We'll zoom in on a little bit. That's our original triangle, centered at 0, negative omega m, positive omega m. What are those frequencies? And those frequencies? Keep in mind that we're modulating by this c of j omega, which has impulses located where? Our triangles will be located right where the impulses were. So where is this impulse located? This is k is 0, this is k is 1, so this will be omega naught, or 2 pi over t. This is k of negative 1, so negative omega naught, or negative 2 pi over t. So if we don't want these triangles to overlap, we need to make sure that this point stays greater than this point. What will this frequency be? Now that we know this frequency, what will this frequency be? It's a distance of omega m from the center of the triangle, so 2 pi over t subtract omega m. So what condition do we need so these two triangles do not overlap? We need this frequency to be strictly greater than this frequency here. Again, a little bit of algebra. And this should look very similar to Nyquist, where omega naught is greater than 2 omega m. Note that this is a different condition than we had with sinusoidal amplitude modulation, because in that case we did not have this triangle, nor any of these triangles, so there was more space between this triangle and this triangle before they overlapped. We were really much more concerned about triangles overlapping when we did frequency division multiplexing. Okay, now on to time division multiplexing and demultiplexing. Remember we had frequency division multiplexing before, where we're trying to fit the spectrum for multiple signals in our frequency space. But now we want time division multiplexing, which means we want to fit multiple signals in our time space. Well, notice there's all this gap in between our pieces of signal. In that space, there's room to put something else. We can use it. So we'll take another signal. We'll modulate it by a rectangular pulse train, but one that's on when our original one is off. Our signal would multiply by 1 to give us our signal value here and a 0 value here. Our signal value here and a 0 value here. Signal value here, 0 value here. Signal value here, 0 value here, etc. So that's our result. Notice we are not restricted to our signal being positive. It doesn't matter for this sort of modulation. And that signal, once modulated, will fit very nicely in between the non-zero components of our other signal. And as I've drawn it, there's room for even another one here. And if I made this a little bit narrower, we could fit several more in here. They do need to have the same period, though. Okay, how do we get our signals back? We want to separate these. What do we have to do in order to separate our two signals? Send it on two different paths, and then what to each? For this one, again, multiply by a rectangular pulse that's on when the gray one is on and off when the others are on. And likewise, multiply by one that's on when the orange one is on and off when the other ones are on. This process is called multiplexing. This process is called demultiplexing. But this time, it is time division multiplexing because we're separating things in time. What happens in frequency when we add all those pieces? The spectrum for our original signal was that sync shape, a repetition of triangles, or whatever spectrum shape we've got for our original x of t. x2 of t will have a different spectrum, perhaps a semicircle. Not really, but it's easy to draw. And that will also follow a sync pattern. When we add them, this is located at 0, this is located at 0. They're going to fall right on top of each other. That's okay, because it's in time is when they're separated. Just keep that in mind. Okay, a short aside. How did we build these, or how could we build these? We've got digital electronics now, but how else could we do this? Historically, we would have a motor turning something which had a conductor and a non-conductor that would pass by a brush and make contact when the conductor was there and not when the other one was by rotating. So it would alternate being on and being off with a given period in a given duty cycle. So let's look at the whole process again from the very beginning. We have our modulation, but this time with a rectangular pulse train. Then our multiplexing. Then our demultiplexing. Then our demodulation. Again, make sure you can draw everything that's on each of the wires here and fill in values.